Hey everyone, ever stared at a mass spectrum in your textbook and just felt completely lost? You are not alone, but you're in exactly the right place. In the next few minutes, we're going to crack the code on these graphs so you can walk into your AS chemistry exam, see one of these, and know exactly what to do to get those top marks. So, what even is this thing? I know, at first glance, it just looks like a bunch of random spikes on a chart. But this is a mass spectrum. You can think of it like a molecular fingerprint. Every single line, every peak is a clue. And once you learn how to read them, well, it's a guaranteed way to score big in your exams. Now, before your brain starts to melt thinking about magnets and ionization chambers and how the machine actually works, I've got some fantastic news for you. And this is straight from the CAI syllabus itself. It says, you don't need to know how the mass spectrometer works. Phew, what a relief, right? So yeah, forget about the engineering. Our mission today is simple. We're going to become expert code breakers. We're focusing only on how to read the results, the graph itself, to pull out all that juicy chemical information and turn it into exam points. Okay, let's dive into Level 1, cracking the elemental code. This is all about using a mass spectrum to find the relative atomic mass of an element. This is the absolute foundation, and trust me, it's a super common exam question. So why do we even see different peaks for a single element? Well, it all comes down to isotopes. Just a quick refresher, isotopes are atoms of the same element, so same number of protons, but they have a different number of neutrons. And that difference in neutrons means they have a different mass. All right, let's get our hands dirty with a classic exam-style problem. Imagine the question says, a sample of gallium is analyzed. Use its mass spectrum to calculate the relative atomic mass, and it gives you the data. You've got a peak at mass 69 with an abundance of 60.11%, and another peak at mass 71 with an abundance of 39.89%. Our job is to find the relative atomic mass. And guess what? There is a simple, foolproof, three-step method that works every single time. Step 1, multiply each isotope's mass by its percentage. Step 2, add those results together. And step 3, divide that big total by 100. That's it. Let's see it in action. So let's apply our method. For the first isotope, we do 69 times 60.11, which gets us 4147.59. For the second one, it's 71 times 39.89, which is 2832.19. That's step 1 done. Step 2, add them up. That gives us a grand total of 6979.78. And now for the final easy step. We just divide our total by 100. So 6979.78 divided by 100 is 69.7978. Now, the exam will usually tell you how many significant figures to use. 3 is pretty common, so our final answer is 69.8. And just like that, Level 1 is complete. See? Not so bad. All right, time to level up. We're moving on from simple elements to the fun stuff, organic molecules. Here, we're going to learn how to identify the whole molecule using something called the molecular ion peak, and then figure out its structure by looking at the pieces it breaks into. Okay, this next bit is absolutely crucial. It's the molecular ion peak, or M+ peak. This is the star of the show. It's the peak with the highest mass-to-charge ratio, or MZ value. That basically means it's the heaviest thing detected, so you'll find it all the way over on the right-hand side of the graph. And here's the magic part. Its value on the x-axis is the relative molecular mass, the MR, of your molecule. Let's use propanone as an example. If you saw its spectrum, all you'd have to do is scan your eyes to the far right, find that last major peak, and look down at the number. Boom, it's 58. In literally 1 second, you have found the relative molecular mass of propanone. It's that powerful. So if that last peak is the whole molecule, what on earth are all the other ones? Well, they're fragments. The spectrometer is a pretty violent place. It smashes molecules apart, breaking their bonds. These smaller, charged pieces also get detected, and they create that unique fingerprint we talked about. For propanone, you'd see a big peak at 43. That's probably a CH3CO fragment, and another at 15, which is just the little CH3 group. These fragments help us confirm the molecule's structure. Welcome to Level 3, the expert level. This is where we learn to read the secret messages hidden in those tiny little peaks right next to the big ones. Honestly, mastering this is what separates a good student from a great one. So, have you ever looked really closely at a spectrum and noticed that tiny little blip, just 1 unit to the right of the main molecular ion peak? That's called the M+1 peak, and it's not a mistake. It's a super important clue. Any idea what might cause it? It's another isotope, but this time it's carbon-13. You see, while most carbon in the universe is carbon-12, about 1.1% of it is the slightly heavier carbon-13 isotope. This means that in any sample, a few of your molecules will naturally contain a carbon-13 atom, making them one mass unit heavier. How cool is that? It just shows you how incredibly sensitive these machines are. And we can actually use this tiny peak. The CIE syllabus gives you this powerful formula. All you do is measure the height or the abundance of the M+1 peak and the M+ peak, plug them into this formula, and it will tell you the exact number of carbon atoms in your molecule. It's like a secret weapon for solving structures. Okay, so what if you see a peak 2 units after the molecular ion? Well, that's the M+2 peak, and it should be like a giant flashing red light in your brain. When you see a significant M+2 peak, you should immediately think halogens, specifically chlorine or bromine. And what's great is that they leave behind unmistakable fingerprints. If your molecule has a chlorine atom, the M+2 peak will be about 1/3 the height of the M+ peak, a 3-to-1 ratio. Why? Because the chlorine-37 isotope is about 1/3 as common as chlorine-35. And if you have a bromine atom, the M+2 peak will be almost the exact same height, a 1-to-1 ratio, because its two main isotopes, bromine-79 and 81, exist in almost equal amounts. Okay, we've gone from level 1 all the way to level 3. We've covered all the theory. Now let's put it all together into a simple, clear, battle-ready attack plan that you can use the second you see one of these graphs in your exam. Here it is, your 4-step checklist. Step 1, find the mister. Look for that M+ peak all the way to the right. Step 2, count the carbons. Use the tiny M+1 peak and the formula. Step 3, spot halogens. Look for a significant M+2 peak and check the ratio. Is it 3-to-1 for chlorine or 1-to-1 for bromine? And finally, step 4, identify fragments. Use those other big peaks to confirm the pieces of the puzzle fit your structure. That's it. Follow these 4 steps every time. And that's all there is to it. You now have the complete 4-step plan to take any mass spectrum from a confusing jumble of lines and turn it into a source of easy marks. So next time you see one in an exam, don't panic. Just follow the plan. Ready to master mass spectrometry? You absolutely are.